Last class, we started talking about the vocabulary associated with sinusoidal functions. We're going to annotate this sine wave right here to make sure we remember all of that vocabulary. First of all, how do I know that this is a sine wave? Starts at 0, 0. And yes, we're going to be shifting these graphs up and down, which you also saw last class. So instead of saying sine starts at 0, 0, we're going to say sine starts at the midline. Because for a typical sine function, yes, that's 0, 0. But we can shift this up and down, so we may not always have it starting at cute 0, 0, but it will be at a midline. On the other hand, if it was cosine, where does it start at? At the maximum. So it's going to start up at the top of the wave for cosine. Yes, that means it can start at a minimum, because that would just be a reflection of cosine, but it's going to start at a maximum. That's what we're going to tell ourselves. If I were to show you this distance right here, and I'm not using color on purpose here, I would recommend not using a bunch of color. What is this called, that distance? The period of the graph. So that's how long it takes for the graph to repeat. For a typical sine wave, it is 2 pi. If I flip that value over, it's called the frequency. It's how many waves I get in a typical 2 pi period. If I show you this value right here, this distance, what is that called? I don't think anybody saw me draw it because you were all writing. This one right here. I heard somebody whisper it. Amplitude. It is the depth or height of the wave from the midline to the max or midline to the min. We also talked last class about sine being the odd function as long as it goes through the origin. Cosine is what kind of function? Even, as long as you can fold it on the y-axis. And then there's a few more pieces of vocabulary we technically didn't talk about last time, but I want to bring to your attention. They're not new. They just still apply to sinusoidal functions. If I'm looking right here, this is where this graph crosses the x-axis. What's another word we've used for where the graph crosses the x-axis before? X-intercept, cool. It is the origin. What else? There's 4 words that mean the same thing. So you've already told me x-intercept. These are your rocks words. If anyone remembers that from Algebra 1. Your roots, your zeros, your x-intercepts, and your solutions. The one we're going to use the most often in pre-cal is the 0 of the function. It's because the y value is 0, so the x is considered the 0 of the function. What is this called for any particular function? It's like at the top. Maximum. Okay. And then we come back down. What happens right here? What is that called? We've already written it down once. It's another 0. Okay, interesting. And then we have this guy. What is this one called? A minimum. And then we go back up. What is this guy called? 0. So if we notice this pattern, we're oscillating back and forth between the maxes and mins, crossing through the zeros every time. Now that's again for this graph because it's situated exactly on the x-axis. It's odd. It's an odd function because it's situated on the x-axis. But what I want you to do today is start thinking about these as the separate steps of the function. We go from a middle to a maximum, middle to a minimum, middle to a maximum, middle to a minimum, middle to a maximum, middle to a minimum, over and over and over again. Those are the steps of the function. That's what I'm going to call a step. It's not a vocabulary word, it's just what I'm going to refer to it as. Every step is a different length. Okay, they're even length steps going from one characteristic to the other. Now what we're going to do today is we're going to work on writing sine and cosine functions as transformations of these parent functions. So functions, and I've already got mine color-coded, so if you want to grab red, blue, green, purple, that's the colors I'm using all day, like all day. I recommend that. Functions that can be written in these forms, and you'll see mine is already color-coded, like I said. A, B, and C are going to be real numbers, meaning not imaginary numbers. And the A value just cannot be 0 because you're multiplying by 0, then it's no longer a sine function. we can create all of the transformations that we studied since Algebra 1 for these functions as well. They just have different names because they're sinusoidal instead of just regular functions. I'll give you a second to color because I know everybody's just sharing the colors right now. I'm just going to pause it right here so you can see what I've done. So we can take these sine and cosine waves and apply the different additive and multiplicative transformations, which are the transformations you've learned about from Algebra 1, to create different versions of sine and cosine. On your homework from last time, you already saw some versions of this where I had the graph like lifted up because the midline was up or the midline was down. It was really high frequency or really low frequency. Those are different transformations. We're actually going to use vocabulary to speak about transformations today, though. The main important thing to remember is that sine and cosine are actually just transformations of each other. We talked about last time that we can shift sine by pi over 2 radians to the left to be able to create the cosine function. They are 90-degree differences from each other, or pi over 2 radians. So let's talk about what happens for each of these numbers as we change them. If I change the a value, the number in front of the entire function, like always, that creates a vertical dilation. That's the same it's been since forever. And the vertical dilation is going to be absolute value of a. The reason I say absolute value is because if a is negative, that means it's a reflection. It would flip over. We get that. But the a is going to tell me how much to stretch or to shrink my graph vertically. Pull it up or pull it down. Which means since I'm stretching the graph vertically, that is going to affect the amplitude of this graph. So the number in the very front changes your amplitude, changes how big or how deep your waves are. The b value, which is inside the function, since it's inside, we know it's going to be some sort of horizontal transformation. And since it's multiplied, this creates a horizontal dilation. It's also on the inside, so we have to remember to do the opposites. So it's a horizontal dilation by a factor of absolute value of 1 over b. The absolute value takes care of the fact that if it's negative, it's just reflected over the y-axis. But we're looking for the b value to talk about how much I have stretched or shrunk it horizontally, like an accordion. Now what that changed for my sinusoidal function, it affects the period and the frequency. So the letter B is going to be used when we talk about the period and the frequency. Remember, we are checking to see how many waves occur within 2 pi for my frequency. So if I have a number where B is, it's going to change and no longer have 1. It might have half of 1, or it might have like 8 waves in 2 pi, high frequency. The C value does what it's always done. Since it's added on the inside, inside means it's a horizontal transformation. And since it's added, this is going to be a translation. Now this horizontal translation, again, because the function we are going to use already says plus C, which is different from how you've done transformations horizontally in the past, our horizontal transformation is a negative C direction. Now what this affects is a new vocabulary word for you today. It affects what's called the phase shift of the graph. It is going to move your graph left and right. Now hopefully what you're thinking is, oh, when we moved our graphs left and right last time, sine could become cosine or cosine could become sine, which is exactly what phase shift does. It is how sine can become cosine and cosine can become sine. It's going to allow me to shift back and forth between these two types of functions. Phase shift. Now because this one's a little bit different and a little bit confusing, let's write a little bit of extra information for ourselves. For a horizontal translation, and this has never changed, if you see a plus sign in your formula, it's going to move the graph to the right. That's a lie. It's going to move your graph to the left. See? I got to slow down, Kath. All right. If you see a minus sign in your formula, it's going to move your graph to the right. That is the same as it has always been – since we started learning transformations. The other thing I want you to write, and this is not going to make any sense to you right now, but because I know this is where you'll look the most in your notes when you're doing your homework, we're going to write the following. If you if you know it's sine, but looks like cosine, you are going to take one step left, which is going to be a plus. This makes no sense yet, but I promise you when we do examples, this will make sense why I'm having you write this down. If you know that the function is cosine, but the graph looks like sine, you are going to take one step right, which is a minus. Again, that makes zero sense to you right now. I fully get that. But that will be helpful for you later when you start to do your practice problems. The letter D in the function is added at the end. Whenever we took regular functions and we added numbers at the end, what we did was we vertically translated them. We vertically translated them the direction that D says. So plus goes up, minus goes down. That's going to be the exact same for us, but in a sinusoidal function, that affects the midline of the graph, which makes sense because you're going to take the whole sine wave and scoot it up, or the whole sine wave and scoot it down. So you're moving the midline of the wave. That's what you're vertically translating. So if I ask you for information about the amplitude, the period, the midline, the phase shift of different transformed functions, all you have to do is know these formulas. The amplitude is just the absolute value of A. The period, this one has a formula, is 2 pi divided by the absolute value of B. The midline is y equal to D. And the phase shift has to do with the C letter. So all of the vocabulary I learned about for sinusoids, yes, I can get from the graph, but I can also get from the equation. I can know what's going to happen to my waves. One last thing before we go. Dealing with the period and the B and the frequency, you need to know the value of B upon occasion. So if I were to ask you to solve for B, and your formula right now says period equal to 2 pi divided by B. I'm going to lose the absolute value bars for right now on purpose. I want this to say B equals instead of period equals. So what do I do on both sides? Multiply by B. So after doing that, it would say B times the period equal to 2 pi. And so if I finish solving for B, what is B equal to? What do I have to divide by on both sides to get B by itself? The period. This formula right here, B equal to 2 pi divided by period, is just a derived formula for B, which will come in handy because we're going to be needing to solve for B in different problems. Because I'm going to ask you what's A, B, and C, and D. Now, obviously, I just have sine function here on your paper, but literally all of this is the same for cosine since they're just phase shifts of each other. So everything we put on the front page, even though it says only sine, works for cosine as well. Let's see some example problems to figure out what I'm even talking about here. On the back, this example 1 says the following functions can be written in the form f of theta equal to a sine of b times theta plus c, all of that plus d. Highlight that right now. What kind of function am I dealing with right here? Is it sine or cosine? Sine. You have to know, based on the formula that I'm telling you the function is, whether it's sine or cosine, because that changes your phase shift. We are going to determine a, b, c, and d for each of the following graphs. Let's start with A. First things first, what kind of function is A based on the way that it's graphed? Is it sine or is it cosine? Sine. How do we know that? Starts on the midline. It's also from your homework, so you've seen this before. Okay, we know that this is sine, so we know we're not going to have to do any sort of phase shifting to get it to be a sine graph. If we start listing out A, B, C, and D, we know that A would be my amplitude, B would be having to do with my period, C is the phase shift, and D is the midline. A and D are the easiest to see. What is the midline of this graph? 3. So D is going to be equal to 3 because that's the midline of my graph. That's the midline. What's the amplitude of this graph? Ooh, remember, it's only from the midline to the top or midline to the bottom, not the whole distance. 3. Because this right here is my amplitude. Those two are the easiest to find, especially when you have a graph, because you can just look at it and be like, 1, 2, 3, or where the middle is. Okay, if you're like unsure, here's how else we could have done this. We had a formula for amplitude that was the maximum value minus the minimum value divided by 2. That's 3. This, you're just looking at the midline, and since the midline was y equal to 3, D value is 3. Now you guys noticed earlier that this was already a sine function. And if I have a sine function, I'm trying to write a sine function, that means there is no phase shift. That's not how you spell that word. Shift. No phase shift because it's already sine. I don't have to scoot it around left and right. But B is always going to be the challenging question because we can't just look at the graph and be like, that's B. We need to find B. But we have a formula for B. We said that B is going to be equal to 2 pi divided by the period. Period is something I can look at this graph for. What is the period of this graph? How long does it take for the shape to repeat? If I look, let's just say here, the next time I get that same shape is right here. How long is this? Half of pi, pi over 2. So I'm going to do 2 pi divided by pi over 2. The pi's will cancel each other out. And then I have a fraction in the bottom. We keep change flip, which means this is really doing 2 times 2, which is 4. So the function, if I were to write it, which it just says find A, B, C, and D, it doesn't say plug them in, it would be 3 sine of 4 times theta, close parentheses, plus 3. That would be the function, if we typed into Desmos in our calculator, would return this shape. Cool? I'm going to scoot this over just so I don't run out of space on this guy. For number B, we're still doing this one together. What kind of function is B? Cosine. We know it's cosine because it starts at a maximum. So that's going to be an issue for us later. We'll leave that problem for future us. Let's start with the easy stuff. A and D are going to be really easy to find. So I'm going to start with A and D. I personally like starting there. Where is the midline of this graph? -4. So my D value is going to be -4. -4. The amplitude is the distance or the depth of the wave. If I go from here to here, how far is that? 1.5. So we can write at 3/2 or 1.5. Since that's a fraction that you don't have to round, it's a nice pretty fraction, you can give me fraction or decimal. Sometimes it's easier to work with others. Okay, but then we have B and C. Oh boy. B requires a formula. B says that B can be found by 2 pi divided by the period. What's the period of this graph? How long does it take for me to go from a maximum back to a maximum? 2 pi. So I'm going to do 2 pi divided by 2 pi. What is that equal to? 1. So B is 1. The C value, though, is going to occur this time because we notice this looks like a cosine function, but we want to write a sine function. We need to shift the graph by a certain amount. We need to shift the graph one step. Which direction? If it looks like cosine, but you're writing a sine function, if we flip back to the front, one step. Did I write down right? It should be to the left. All right, so we need to take one step left. Now, what is a step here? I said earlier, a step is going to be one jump between a 0, a max, a 0, and a min. So if we're looking at our graph here, I'm starting at a maximum, and here's my next 0. How far is this step right here? If this is 0 and this is pi, what's this?
Pi over 2.
Pi over 2. So we're going to make our step pi over 2. We're taking one step to the left. Left is a positive number. Okay? Pause for a second. I want you in your table to go back through how I got A, B, C, and D for these first two in example 1. Just make sure there's no questions about where A, B, C, and D come from before we tackle the cosine functions. Are there any questions we would like to ask out loud? I know I went around and answered some, but are there any more we want to ask out loud? Yes? The C part? Okay, in number 1, in part A, what? How do I say that? In the first graph, this one looks like a sine function, yes? We are writing a sine function. So we don't have to shift it at all because it looks like a sine and it is a sine. So the phase shift is 0. There's no side-to-side movement. But in the second one, you guys notice this looks like a cosine function, but I want to write it as if it's a sine function. So I have to shift it from side to side to force the waves to look right. So what I do is I shift by 1 unit, 1 step, from a maximum to a 0. 1 phase shift. And so for this one, the step, again, that's not a vocabulary word that you would get out of a textbook, but I'm going to call it a step. 1 step would be from a maximum to a 0, which is this distance. This distance is half of pi. So it's pi over 2, half of pi. And it's positive because we're writing a sine from a cosine, so it's positive. This might be easier, actually. I'm going to redraw where I put this green part because I think I'm misleading you with that. A sine function starts immediately going up. So like if this was a sine function, this would be the starting place, correct? The sine wave goes up, then down, then up again. So if I want that sine wave, up and down and up again, to be here, I have to move it this direction to the right, which means it's plus. It's a positive number. Can we try a couple more examples? Okay. In example 2, this time we are writing what types of functions here? Cosine. All right. So if it looks like a cosine and we're writing a cosine, there will be no phase shift. If it looks like a cosine, if we're writing a cosine but it looks like a sine, we're going to have to phase shift. In the first one, what does that graph look like? Sine or cosine? Cosine, because it starts at either a max or a min. This one's a min, which will make a difference in this problem. So let's go ahead and take care of the easy ones. We're going to have A, we're going to have B, we're going to have C, we're going to have D. D is the easiest. What is the midline of this graph? One half, yeah. So 1/2, or since that's a nice pretty decimal, you can say 0.5, because that's where the middle of the graph is. The amplitude is pretty easy as well. What is the distance from the midline to the top of one of those waves? It's just 1. Now here's the deal, and this is where I confused Jimmy earlier. Jimmy was like, wait, but cosine starts at a maximum. How do I get it to start at a minimum then? If it normally has this one up here, what do I do to it to flip it down there? Reflect it. Oh, so A is going to be negative because we've reflected it, which means we made it a sad graph. So we made it negative. Okay, let's handle the B value. B has a formula. B is 2 pi divided by the period. What is the period of this function? How long does it take to go from minimum to minimum? Pi. So B is going to be 2 pi divided by pi, which is what? 2. So B is 2. C is your phase shift. We are writing a cosine function. Does it look like a cosine function? Yes. It's 0. There is no phase shift when you are writing the type of function it looks like. B and C are, yes, more confusing. A and D should be in the bag. We got those. Let's try this other one. What kind of function does this one look like? Sine. So in our head, we're like, all right, there's going to be a value for C. Let's take care of the easy stuff first. Let's do A and D. What is B? What D? What? Oh my gosh. All of the letters are floating around in my head. I can't say the right one. What is the midline of this graph? -1. Yes. So if I look where the middle is, it's at -1. I've scooted it down 1. What is the amplitude? 1/2. Because the distance from the midline to a maximum or the midline to a minimum is a half unit, or 0.5. Let's handle B and C. All right, B has a formula, 2 pi divided by period. So what's the period of this graph? How long does it take to go from, and sometimes it's easier to just look maximum to maximum. Let's do that, maximum to maximum. How long is that? Pi. So this is going to be 2 pi divided by pi again, which is 2. We already did that math. Oof, and then we take a deep breath. We're going to do the phase shift. I told you to write a cosine function, but it looks like a sine function. So we need to take a step in one of the directions. We're going to take one step right. So we're going to do one step right. Now, what is a step here? A step is the distance from one characteristic to another. So from, and I'm going to zoom in on this one, a 0 to a maximum. Let me not overdo the number. What is that distance right there? Pi over 4. So my step that I'm going to have to phase shift by is pi over 4. But because, make sure we write that down right, but because we are writing a cosine function when it looks like a sine function, to go to the right, I'm going to have to put a minus sign right there. So it is a negative direction, negative C. Cosine becomes sine. If you're writing cosine, it looks like sine, it's negative C. If you're writing sine, but it looks like cosine, it's a positive C. And those are the two differences there. That is confusing, and it's hard to keep track of. Yes?
Can you explain why you put a -1?
For this one?
This one.
Yes, I'm going to actually show you on an actual graph. So yes, Desmos is your friend on here to see. It's I know you all have graphing calculators, but because of the way you're wanting to shift the graphs to see the numbers, it would be easier while we're learning to use Desmos. We'll get to the calculators later. Last page, last page. Now, if you notice, we did this problem, for the most part, on topic 3.1. And in fact, I already wrote all the answers that we did on 3.1. We don't have to redo the whole FRQ3. But I told you when we did topic 3.1 that there was actually another question in the center that's actually question part B. And we skipped it. Well, now we can answer it. Because if you remember, in this problem, we had a clock. We're measuring the distance of the end of the, oh my gosh, what is that called? Arrow? No. What am I thinking? Hand. Thank you. Oh my gosh. The end of the hand. It goes down. It comes back up. That's a wave. So when we did this problem, we said, all right, if the period is 30 minutes, that's what this tells me because it's a broken clock, then we know that in one full wave from start to finish, it's going to take me 30 seconds. Do y'all remember doing this? Okay. We also said that the amplitude of this, we didn't know that word then, but the amplitude was 8 inches because that's how long the clock hand is. So this would be 8 inches, this would be 8 inches, this would be 8 inches. Which is how we got these numbers. We also said that the center line, the center of the clock, is 120 inches directly above the center. I just used all of the wrong colors. I am so sorry. I'm going to redo it, and I know that's going to bother you. This should have been red. I'm sorry. I'm sorry. I'm the worst. This should have been blue. I'm the worst. I know. Okay. This is why I suck. Okay. Okay. I'm so sorry. Do y'all remember doing this back when we first started back in January? Okay. We found all of the possible coordinates around this graph for F, G, J, K, and P. We know that the period is from start to finish, so start to finish should take 30 seconds. This is 0, this is 30. That's the period. We also knew that the midline would happen in the middle, so K and G had an output of 120. We found the other numbers by adding 8, my amplitude, subtracting 8, my amplitude, and adding 8 again, my amplitude. These numbers just came from the even spaces or steps around the graph. Every step. What we can do now is answer part B of this third FRQ. It says the function h can be written in the form h of t equal to a times sine of b times t plus c, all plus d. Whew. We're wanting to find the values a, b, c, and d. It will always ask this, to find the values of a, b, c, and d. Your job is to make sure you know how to do this. What kind of function am I having you write? Sine. Based on the fact that this is 0, is my graph, air quotes, sine or cosine? Let me help you out. This is going to be your y-axis right here. Cosine. So are we going to have a phase shift in this graph? Yes, because it wants sine. My graph looks like cosine. But this is not going to be that bad. Okay, let's do our amplitude. So A, what is the amplitude of this graph? 8. That's how long the hand of the clock is. That's how long the lever is. We can do max minus min, divide by 2, we would get 8. Let's go with the other easy one. What is the D value? 120. Now we just need B and C. B has a formula. To find B, we do 2 pi divided by the period. What was the period of this graph? 30. 2 pi divided by 30 reduces to pi over 15. That's B. And then I need to do my phase shift. We know we have to phase shift because it starts at a maximum, but this is sine. I'm going to write a note for you here. So the clock starts at a maximum, which means it looks like cosine. But this function is sine. So we have to shift it. We need to shift it by 1 step left. What is a step here? A step is the horizontal distance from F to G, from G to J, from J to K, from K to P. What is one step?
7.5.
Boom, 7.5. So you technically have already found most of these numbers in part A for part B. That's 2 more points. Okay, part C, again, we answered this on our last note, so I'm not making us do exactly again. We said that on the interval from G to J, this one is saying from G to J, it wants to know if H is positive or negative and if it's increasing or decreasing. As a review, if you look from G to J, that's here. Is your clock at that point above the ground or below the ground? Above. So we know it's definitely going to be positive. We wouldn't answer H as negative. We're getting positive values. The Y outputs are positive. And on that section, is it going up or going down? Down, so it's decreasing. That's why we chose answer choice B. For part 2 of part C, it asked me to describe the rate of change. On that section, it's hard to show both, we would notice that it is concave up, which means that the rate of change is increasing. Those are the keywords we're looking for. Concave up, rate of change is increasing. Not the function is increasing, the rate of change is increasing. So I was really focused on part B here because that's what we've just learned is to identify A, B, C, and D. But now we can answer the entire FRQ3. We know how to handle part A, part B, and part C.